Hello everyone, this is Kuldeep Jivani. I work as a research data scientist and a data science architect. Today we're going to talk about the research that we did on finding the optimal kernel density estimation using the FFT based cost function. So at a high level, we are going to talk about the following things. First, what this leads to and where can we apply the kernel density estimation. Then what exactly is the kernel density estimation. Then we'll talk about some of the existing bandwidth selection strategies. And then we'll move on to the proposed algorithm and the current techniques. Then we'll define the experiments and we'll come to the results and the conclusions. So just let's start with it. At a very basic level, when you talk about non-parametric density estimation, the idea is, let's see if we have a single one-dimensional data. We want to find the density of that. So we can get a PDF that tells how the data is distributed. We can do the same thing for a multivariate data. Let's say we have a two-dimensional data. We can again get a density estimate using non-parametric techniques, where we are not assuming any specific form of the data and we just obtain directly from the data. So that's an idea of a non-parametric density estimation, and that's where KD comes in. And the applications for this kind of technique is multiple. Firstly, it's like EDA, the exploratory data analysis, where we look at the data distributions and understand what the patterns of the data are. Then we have other application areas like anomaly detection. We can normally use parametric forms to get the anomalies, like we use a z-score to put a threshold, and based on the parametric forms like the Gaussian distribution, we get the anomaly value. But most likely in real world, the data may not be normally distributed. It may have different forms. So at that point, we would need a generic probability density estimation, like a non-parametric version, which could be even multimodal. So this is where the KD helps in. And let's say we have a case like this, the values in between are also anomaly, which maybe a normal parametric system may not be able to find. But yeah, would be able to find. Then the other applications of this could be like clustering, where we do a density analysis of the data and find the high dense areas. So mostly the high dense areas are related to the clusters. So this is helpful over there. So now let's look at the density estimation techniques which are used in literature. So at a very general high level, the idea is we have a kernel function. So we want to take the contribution of each point towards the whole density. The way we do it is, let's say we have this kernel function. So we want to sum it over all the points, and the kernel defines how the spread of a point comes to the other different points. So if we replace k by the kh notation as shown over here, we can use a Gaussian kernel where the kh would be equal to the standard, the normal distribution with xi as a center and h as the variance. So for each point, we'll use a different distribution function with a different center and the same variance as square. So the combined effect of all these kernels will generate the PDF, and where h is the bandwidth of the kernel, that will be effectively controlling the variance or the spread of each point, how it affects the other points in the kernel. Visually, if we just look at this picture over here, let's say we see the green points below. So each of these points will fit a normal distribution or a Gaussian kernel over here as centered at this point, and the h will determine how far the effect of this point will spread to the other points. And when we sum up all of these, let's say these red curves are the individual distribution of these points, and eventually the sum is the blue curve. So this red curves are the kernel functions, and eventually we get the final probability density function, this by summing up all of these. So that's the general idea of using a kernel to determine the density estimate. As you can see, the h or the variance is a very sensitive parameter, and the whole density estimate can vary a lot with different values of h. So for a very low value of h, as you can see on the top left chart, the density estimate is very precisely fitted, or we can say it's overfitted to data points. if we increase the value of h, we see kind of a smoothing happening, and we see some kind of a trend over here, which makes some sense. But as we further increase the value of h, we kind of lose the trend but get a very generic shape. And for a very high value of h, we just get a normal distribution. That's it. We just lose all the information that we have, and we can't infer much from that. So this is, we can see h is a very important parameter for density estimation, and so we need to figure out the right value for h. So this h also determines are we underfitting or overfitting the density estimate. Like if you can see in the diagram below, if we use a high value of h, we'll most likely have a normal distribution and skip the actual distribution. So this will be like more like a bias. So the true density would be much different from what we have estimated. On the contrary, if we have a low value of h, then we will have a very high overfitting scenario, and the actual estimate would vary a lot, and we'll again miss the actual true density estimate. So both of these are problematic scenarios. So what we want is like a balance between them, not too high bias, not too high variance. How could we achieve all those things? So in the literature, we have many such techniques where people have done these kernel density estimations. So I'll quickly summarize the main crux of finding the kernel density estimate. What we do in general is like minimize the estimation error by using the MISE, or which is the mean integrated square error obtained via the expectation of the integrated square error. So for minimization purposes, we need an asymptotic MISE, which we can obtain via if we have h tending to 0 and nh tending to infinity. So we get this term on the right, that's the h MISE. I won't go into details of this derivation. Let's assume this is the form and quickly look at the derived forms from this general expression. So the one of the popular rules or the equations used for obtaining the h is called the rule of thumb. So this is obtained when we approximate the RF double prime via a normal distribution, and with mu k equal to 1 and rk is 1 by 2 root pi. So the equation we get is the following, and this equation is very popularly used across many software packages. If you are using Python, then all the kernel density plots are basically using this in the background. They have an option called the Silverman or Scott. Both are actually same, just the value of this constant changes in Silverman and Scott. But yeah, this is the default formula used in the KDE packages by Python. But there are more algorithms which are more complicated, like the least square cross validation, the bias cross validation. They have a strategy of like leave one out and then validate. I won't go into details of this, so we'll just quickly look at the list of these techniques. So the another one is called the DPI, or the direct plugin by Shether and Jones. This is a quite popular technique. This is a kind of an extension of the RT technique which we just saw above. This is the estimate or the approximation is not at the first stage. Like in RT, we approximate RF prime at the very first level by a Gaussian distribution. Here, we do multiple iterations of data before plugging in the estimate or of RF double prime. So this actually helps us in obtaining a good trade-off between the bias and the variance. And this is like a very good technique which is used popularly, and it's also available in the R package by the name of SJ. So this is a popular technique. Then let's look at some of the strengths and weaknesses of these techniques. Like RT is quick and simple, that's too easy, but it tends to do over smoothing or give bandwidths which are too large for non-normal data. For the cross validation based selectors, they're more suited for highly non-normal data and rough densities, because for such densities, the plugin selectors may end up over smoothing. If we look at the DPI one, so in theory, it is expected to better perform than the above two. It has a faster conversion rate, and it tends to be the preferred bandwidth selector in the literature. So we'll use this also as our benchmark to compare our algorithm. So, but this DPI is also sometimes doesn't perform very well when data is noisy. So let's look at these cases. And before going on to the proposed algorithm, I want to quickly cover the FFT based density estimation technique because that would be pretty useful and we'll be using this. So in general, the traditional density estimation technique is like an order n square cost, while the if we discretize data to m grid points, we can bring the cost down to m square. But if we apply FFT, we'll get down to m log m. So via this, we can get this general FFT density algorithm. Where the idea remains, it's like a four-step process: discretize data to equally spaced grid points, and with using the weights of those grids as the grid counts as the weights basically, and then we compute the FFT of these weights to obtain h hat, which is the Fourier transform of the data. Then we compute f hat, which is the Fourier transform of the density, which can be obtained by the convolution of the kernel's Fourier transform and the data. Eventually, what we do is just do an inverse Fourier transform of the f hat to just get the normal f hat x, which is the density of data. So that's a quick way of getting the density estimate using the Fourier transform. So now let's look at the proposed method. I'll just give you the intuition behind this with a high level idea. So definitely we want to have a technique which is purely based on data. Then the idea is we want to have an optimization based technique where we have a cost function which we can minimize, and we want to have some properties for the cost function, like the cost function should be concave so that we can converge quickly. Then the computation should be fast, so we're using FFT so that we have a low computation cost. Then we are using a weighted MAE, or the mean absolute error, where we have a weight function and then we have the error which is computed from the estimated density with reference as the density from the histogram. So f hat h is basically density of a histogram evaluated at the same m grid points where the FFT was computed. So this acts as like a ground reference for comparing the error with the estimated density by FFT. So what we want the weight function to gradually increase the penalization when histogram shows empty bins. So whenever we have an error, the actual evidence is not present, but the estimation is showing that. We want to penalize it with more and more penalization as we go away from the reality. So the metric MAE is better than RMSE because it is not affected by outliers. And this is required at the end boundaries because the density estimation requires a smooth curve fitting so that we have like a smooth continuous function. Then we want the cost function should neither underfit nor overfit, like a balance between bias and variance. So, and then we also want to bound the search space so that we get have less number of steps to search for. So RT acts like a good upper bound for the search. So the idea then remains that we have this cost function CH. We want to minimize this cost function and get the optimal H from this, where we have the minimal cost function value. Then we plug in this H optimal into the FFT density algorithm and get the optimal density estimate. So the cost function will optimize weighted mean absolute error instead of RMSE so that we are not prone to outliers. So this is the cost function. We'll sum up for all the points where we have a weight function and we have the MAE. So the density estimate is computed via the FFT function, and the f at h is the ground difference is obtained by making just a simple histogram over the data using the same grid points. So this function over here for the weight function like 0.1 h square, 0.2 log h is obtained with some values for the constants. So the value 0.1, 0.2, these are obtained via some tuning of the data, or we can see which fits the data. But in general, these values are good enough for majority of data. We may not need to tune them, and this should be good enough. So this has two parts. If you can see, the first part is as a function of h is like a function of h square log h and a constant. Then there is a second part where we have a exponential raised to bxi. That's again a function of x. So bx is simply this number of bins between the current bin and the nearest non-empty bin. So this is a simple function. We have to write in this fashion to have the right computation. But in general, if we have the general form of the weight function, we have these values like h square minus b log h plus c, and then this exponential term. So if the histogram has doesn't have any empty bins, and then the bxi will be 0 for all values of x. So we'll get a simple form as just a square minus b log h plus c. This equation has a minima at b by root 2a. So if we use b equal to 2a, then the minima will always be at 1. This is like a desirable value. We can look later how does it help. But what we want, that the weight function should penalize both high and low value of bandwidth. So we want, so as to avoid the high bias and the high variance scenarios that we discussed earlier. And we also want the error in estimation to be penalized with the exponential growth factor. So the more we are away from ground truth, the more should be penalization. So this is the high level intuition behind the weight function. So if we look at the visuals, so if we have like value of a1, b2 and c0 in the general form of this equation, we get this like a curve. And as you can see, the minima is at 1 because b is equals to 2 times a over here. And if we vary the value of bxi, we'll get the similar curve but with higher and higher values. That means the value of the error estimate will increase as we have more higher values of bx. So this is like the general form of the weight function. And now for the experiment, we took a benchmark data set for benchmarking the data. This is from Medun and Van, a paper in '96. These are like standard normal mixture functions where we have the true PDF available to us. And we can now take random samples from this and compute the estimates. So we have a ground truth to compare. So this is a standard data set. So the way we're going to evaluate this is we'll compare with the most accepted technique in the literature, which is the DPI by Schiller and Jones. And then we'll use scale divergence as an evaluation metric. And we'll compare the scale divergence between the estimated density and the true PDF. Then we'll also compute the KL gain to compare the current algorithm with the Schiller-Jones algorithm. So this number would tell us how much better we are doing with the Schiller-Jones algorithm. So the strategy would be we'll take multiple random samples from the data with different sample sizes and we'll vary n between 2^7 to 2^12. Then we have the also vary the Gaussian noise, because in real world the data would be noisy. So we'll vary sigma from 0.25 to 1.5. Then we'll also vary both of them together. So if you look at the results, the proposed method, as you can see in the graph over here, the green is the proposed method and the yellow is the SJ. So the green is always below SJ majority of the cases. So it implies we have a lower KL divergence. That is, the proposed algorithm is more closer to the true PDF. And in this case, if we keep adding noise to it, if we are, let's say, noise with a Gaussian noise with sigma equal to 1, we can see the green line is even much below the yellow line. If you see the scale also, the scale is larger over here. So we have a much better growth or a much better performance than SJ in case of noise. Now, if we look at the variations, so if we are varying n and looking at the KL gain, so a positive KL gain implies the current algorithm is better than SJ. So we see for n, for smaller values the n is positive, but for higher n the gain reverts. So as in, like when data is too much, then probably SJ does better from this algorithm. But if we add noise, then we can say the KL gain is consistently positive for across all noise levels. So for real world data, this algorithm works much better than the standard popular algorithm available in literature. Now if we vary both of them together, we can again see this chart over here. And as you can see, if we increase both n and sigma, again this algorithm does much better as the value of gain is higher and higher if we increase both of them. So as we can see, when we add noise, the algorithms like SJ, they just don't perform too well. So this algorithm has an edge in the area where we have real world noisy data, which is a more likely scenario to happen. So if we now conclude the entire thing, what we can say, for real world noisy data, the proposed algorithm will perform significantly better than the accepted solution of SJ. And we also compared this with some of the recent papers, and it was still performing better than those. Then the proposed cost weight function is can be basically used to find the optimal bandwidth by keeping both the bias and variance in check. So in short, it can give you a good estimate when you have noisy data, and also it would try to stay close to the true PDF. So this was all we had for this talk. thank you very much